All right. Hello, everybody. Dave Lindberg in Hong Kong with another episode of the THD Podcast. Today we have Dr. Vikrant Tomar coming from Montreal from Fluent.AI. So we're going to learn about speech recognition in any language. A lot of people that are developing voice on the edge type devices are learning that accuracy and recognition isn't always up to snuff. So there's people working on solving this issue. But without delay, we need to not forget our sponsor, the ALTI Association, the Audio and Loudspeaker Technology International. And they've got big ambition this year to actually have an in-person trade show. So coming up October 24th, 25th in Orlando, there'll be a show where people doing audio industry can get together and network in person. So without delay, let's say hello to Simon in Japan. How are you doing this morning, Simon?
Bright-eyed, bushy-tailed.
All right, that's great. And again, Dr. Vikrant Tomar coming in from Montreal. I believe that's correct?
Yes. Hi, everyone, and thank you, Dave and Simon, for having me here today.
Okay, so let's see. So you're originally from overseas, but now you're in Montreal. You started there with your PhD in 2010. So at McGill, is that correct?
Yes. So grew up in India, did my bachelor's in engineering there as well, and then moved to Montreal to further my studies. So PhD at McGill in speech recognition, and original plans were to go back, do something, but then there were the opportunities here. I always wanted to do something, and then I realized there's a big area in speech where there's something needs to be done, and I could contribute. So I started my company here. Okay,
so it wasn't that you fell in love with the winters?
No.
No, okay.
I think there's very, very few people who actually fall in love with Montreal winter. Yeah.
Okay. So this development kind of spawned out of your PhD program into a commercialization step?
Well, it's not the technology itself is not directly related to what I worked on in my PhD, but the overall area is the same. I did work on speech and language processing in my PhD. I also worked during my PhD for about a year at Nuance, which recently got acquired by Microsoft. Used to be one of the biggest name in speech recognition in town before everybody else started doing their own speech. And really why the sort of motivation behind Fluent was, throughout my experience in whether that's during my PhD or during my work at Nuance, and actually I've been working in speech even before that, started in my undergraduate. I was just seeing how everybody was trying to solve the speech recognition problem in the same way. So ASR, they call it automatic speech recognition, to go from speech to text. And then even when all these smart devices started coming along, whether that's Siri, Alexa, etc., sort of people kept the same path. And this is where I saw that there is an opportunity for disruption to have a new kind of technology that could solve some of the existing problems. So the motivation, sort of the experience, that definitely comes from my academic background, but the actual technology, it did not spin out of the PhD work that I was doing. Yeah.
Okay. Can I just ask about the background of speech recognition? So it's been around for a long time. I remember years and years ago, 10 years more ago, you used to have Dragon Dictate, and it didn't work very well, but these things have improved quite substantially. Is there some fundamental changes going on, or it's just refinement?
Right. So, I like to say, and it's not that I like to say, I think it's very true that speech is one of those technologies that's been around, that's been 5 years away for past 30 years, right? So you can always hear it like, it's here, it's so close, we almost have the breakthroughs. Like, people have been working in speech since 1970s. And there were techniques for speech recognition that were the winner or the leading techniques from, I would say, 70s till early 2010s. And it was only with the advent of these deep neural networks and the success that deep neural networks starting to have, not just in speech, but also all sorts of different areas. Primarily, these are relatively deeper networks are possible now. People have worked on neural networks in like 90s as well. They were big at a time, then they died down because people couldn't train them properly. And some of the early breakthroughs that we're starting to have in early 2010s were the same exact model that were there in the 90s. But it's just that now, we had more powerful machines like GPUs to train these models. And so the reason now, since early 2010s, we had the same models that were used in the 90s, but there are more powerful machines, the GPUs, that are now readily available so people could train larger models. And there was also a lot more data, right? So it's the combination of this that started to have big impact. And that impact was not just limited to speech, but you see image recognition, you see really machine learning everywhere these days, right? And that's kind of where it started. So in speech as well, the fundamental changes really starting to happen since like 2012. Before that, people were doing experiments in neural networks or deep neural networks, whatever, but they weren't as big. They weren't mainstream. And since 2012, these things starting to be the mainstream, the main approach. And now there's been a lot of new innovations. But even today, one of the most, or two of the most popular techniques for or neural types of neural networks, convolutional neural networks and LSTMs, they're from the 90s, like 95 and 97. So they're not very new techniques, but obviously there's a lot of new innovation that has brought in all these, all the changes today. So now we can say that speech is actually here, not 5 years away. It's actually here in a usable situation. It's not fully solved, obviously, the problem. That's why we exist. We as in Fluent.AI to solve the problem, but it's in a very, very good shape today.
Okay. So let's just kind of just walk through some things for people watching in terms of, we're kind of talking about the periphery of the barriers to why people are using speech. You're saying it's now here and ready. But some of the things that I think Simon and I have noticed in some of the demos in the last few years are things like accuracy, and specifically for me, accent recognition has been an issue with people developing models in California English, and then the Hong Kong English, it doesn't recognize it, and then of course cost, and then even privacy issues. So I think maybe let's just talk about accuracy. And I know with yours, you're taking out this step of this ASR process. So it seems like you're kind of jumping ahead in terms of like, you're not translating into text and then from text trying to get your identifier and then create an interrupt. It's kind of streamlining that. So it seems like, in a sense, you might be eliminating a lot of problems by not trying to get that ASR accuracy up. You're going directly to trying to get the identifier or classifier out of the voice. Can you talk a bit about how you improve your accuracy?
Yeah, exactly. So let me answer that in two steps. So first, what is the current state of speech technology, where the problems are, and then what we are doing about it, right? So you're absolutely correct that even though we can say that it is here, in the sense, what I meant is there's lots of speech applications you see around you, right? Like we see, whether that's with Alexa, there's actually a proliferation of voice activated devices, right? Or that's with Siri, Google Home, we see it everywhere. But is it still usable? Are most or majority of the people around the world, not just in North America, not just in some isolated space, able to use this technology? And the answer is no. There are a number of reasons. So one of them is obviously accents and languages, right? So I find the comparison of speech recognition with touch interfaces. It's very interesting because similarly when it's starting to have touch screens like in phones and all, it was equally disruptive. And currently all these phones, all devices have these capacitive screens. Before, they used to be the resistive screen, and they were really bad, but they were equally bad for everybody. It doesn't matter where you're from. So now the thing with speech recognition is that for some users it's very good. But if you go to other places, it's bad, either because of accent or because of languages. So there's lots of people who are not able to take advantage of the same technology, right? There's about And there's many reasons for that. The one main reason is the kind of technology that is being used. As I was saying before, the ASR-based technologies, they require a lot of data, it's investment, it's effort, and it's just not possible to do that in all different languages. And there are other challenges, right, with respect to noise. Even all these state-of-the-art technologies that exist, or the approaches in speech recognition, deep neural networks, they struggle in the presence of noise. There's the issue of computational power. Most of the current AI speech recognition stuff still streams your audio to the cloud and then does the processing in the cloud. This raises issues related to privacy. Now everybody's audio is being streamed to the cloud, and we've seen lately a lot of examples where either Alexa recorded somebody's audio and sent it to somebody else, or people were having a discussion at home and they're like, oh, suddenly I'm seeing advertisement of these things, right? So these devices are actually listening all the time. And people these devices misfire a lot more often than people think, actually, but that's a different discussion. So, and the other issue is obviously the cost and latency. Now, if you have to build, for example, a smart fridge, and if you could voice directly in the smart fridge, that's one option. Or if you have to have an internet connectivity option, then that adds additional cost. You need some sort of networking module, you need related software, etc. Right? So those are some of the issues. What we're trying to do at Fluent is really take a step back and think, okay, what we need to do is develop voice user interfaces, right? People like me should be able to go to their device and execute the command. Now, in that scenario, do we really need text? Conventionally, as I mentioned, everybody's been doing speech in the same way. They go from speech to text, then they do natural language processing to extract the meaning from that text. And it works well. We're seeing a lot of examples around us. So it does work well in many cases, but is it really necessary in all the cases? Like if I have a smart door lock, do I need to, and I'm saying lock, unlock, open, close, whatever, do I need text for that? No. The other thing is, think about how humans are doing speech recognition. We're not when I'm speaking, you're not really transcribing it in your head and then trying to understand it. And now you might ask, how do I know? Well, look at kids. Look at people who don't know how to read and write. They can still have fluent conversations in spoken languages. So the technology that we are working on at Fluent is called what we refer to as spoken language understanding, or end-to-end spoken language understanding. So we start with speech and directly extract the meaning from speech. The advantages are we eliminate a number of modules that exist in conventional technology. So it makes our overall system much smaller. And I can give you an example, we are able to recognize up to 200 different intents and many different ways of saying those. So if I were to say that turn on the light is an intent, or turning the light on is an intent, but how I say it, turn on the light, switch the light on, etc., they're just different ways of saying it. So we could do up to 200 those things in as little as 200 kilobyte of RAM, a processor running at 100 megahertz. So something very small, right? So this is tiny. Now, this means that the device manufacturer doesn't have to think about putting an internet connectivity module in their device. They could run everything on the device. It also takes away the problem of privacy because all the processing is happening on the device. And then it also means that it can run on relatively cheaper processors, right? So it can run on very low power, like ARM Cortex M4 or M33 series of processors that are very, very low power. It can even run in hearables. It can run on wearables like smartwatches. So it also enables these new kind of use cases and respects people's privacy. So that's basically our approach towards speech recognition. The other advantage of this approach is it allows us to do some unique things. So think about in a conventional ASR-based system, you start with speech, which is your audio waveform, and then your neural network is trying to map it to the text representation. The text representation is very different than English and then, let's say, Mandarin. So you cannot really, or you can, but it's really hard to put together a model that could understand some commands in English and others in Mandarin. So, but in our case, our neural network is learning to go from speech to meaning. The meaning doesn't change if you're saying your speech in Mandarin versus English, the meaning remains the same. So we're basically also reducing complexity across these building models that could recognize multiple languages. So our approach also gives us these unique advantages. We have models running in 3 different languages on a very, very low power chip. The user doesn't have to go and choose the language. They can just go and say their command in whatever language they want. And this also helps everybody is, or lots and lots of people are bilingual these days, right? People move around a lot. Like I have moved around here. Both of you seem to have moved around as well. The other thing is also cost for the manufacturer in a linguistically dense environment. For example, Europe. I'm a fridge manufacturer. I want to sell a voice-enabled fridge in Germany as well as France. Now, instead of having to worrying about different SKUs for different blocks, I could basically build one SKU that satisfies different requirements and sell it for the single thing everywhere, thereby simplifying the overall manufacturing process. So that's another advantage that our models bring in by adopting this unique approach.
So it just to kind of catch the name Fluent is almost a definition of what you're doing, because the ability to just understand things without having to translate in your head is kind of the definition of fluency. So like, me, my French is brutal. I have to basically translate it in my head and then try to come up with the responses. But the kind of definition of fluent is you're just doing that seamlessly, which is kind of, is that kind of part of where the name of the company came from, or am I thinking too much?
No, you are right. Partly it is, you're fluent in a language when you can really start, when you're thinking about something and you realize like, oh, I'm thinking in this language, that's not my mother tongue, right? You're not like trying to translate it. So that's when you're like, oh, I'm fluent in this language. Or you're dreaming in a different language, right? If you start dreaming in French, that means you're now fluent. So, and this is my opinion. This is not any definition of this word. So some people might disagree, but this definitely similar thoughts went into when we thought about the name of the company, right? Okay. We want everybody to be able to talk to their device fluently without worrying about, it's going to understand my accent or not. What language, etc. Just go and interact.
Okay, and I guess the last thing in the barriers was like privacy, but your machine learning algorithm is basically for edge devices. So I think people can kind of almost throw out the privacy concerns out the window for the most part, because unless it opens up a link to a cloud or some kind of like a something holding memory, it's not going to be recording you, right? Is that correct? It's all happening on the edge, so there's no concern.
Yes, absolutely. So everything is done, all the data is processed on the device itself. Nothing is streamed to any cloud or any other service. So everything we do is private.
Okay. And what are we talking about here? Is it something that you implement on an existing MCU or processor, or is it a separate subsystem chip, or either?
So it could be either. One of our major partner in this is ARM. There's a lots of ARM-based low-power MCUs, and we are supporting ARM Cortex-M4, ARM Cortex-M33. Lots of our customers are running on those, and we can, on M4, we can run our complete. So our two main products are Wakeword and our speech or intent recognition system, right? So, and we can run both of those in 100 kilobyte of RAM. A CPU that's running at 58 megahertz, so something very, very small. But we do, and beyond ARM, we have partnership with some digital signal, DSP chips. We have one of our partner, for example, is XMOS. They make their own specific architecture. They have their own chips. But also there are a number of new NPUs these days, neural processing units. So one of the key consideration when we started building our runtime environment, right? Forget about how we train the models. It's all done in the PyTorch, TensorFlow, these sort of things. But eventually, when it has to go on the device, one of the consideration for that piece of software was that it needs to be very, very portable, because one of the challenge really in this industry is that there is not one configuration of audio device. There's varieties of different configuration, different types of chips, different types of microphone configurations, 1 mic, 2 mic, 4 mics, right? So different kind of signal processing algorithms and all. So we have to interface with those. We have to partner, and we have a number of partners in all of these areas to bring, and so together with our partners, we bring the know-how, expertise, as well as a complete solution for different segments of the markets. Yep.
Okay, and I know one thing that's kind of interesting, and like wind noise kind of suppression and picking up the voice through the wind noise. But I kind of want to make it a two-part question: is using AEC to pre-screen what's coming in. Acoustic echo cancellation, stuff like this, to pre-screen what's coming in from background noise or wind noise. So that's kind of one part, is like the voice application. But I'm also curious if this technology could be used in industrial applications for like things like wear detection in automation, like, or in cars, like detecting vibrations through the audio frequencies that are emitted from like wear. So I guess the first one is tell us about wind noise suppression and background noise suppression, and then tell us if there's any advantages for wear detection in industrial or automotive applications.
So as I was saying earlier, noise is one of the biggest challenge for speech recognition systems, and wind noise is a good example, but like music noise is another good example, especially in scenarios like smart home and all, right? In a typical speech recognition system like ours, the approach is like twofold. One, you work with you have a front end or audio front end that does noise removal. It may do de-reverberation, right? So reverberation is like if you are in it's like a younger brother of echo, right? So if you're in a reverberate, like you sound like you're in a bathroom, you're in a cave, that sort of thing. So, but those basically you're having your microphones are receiving multiple copies of the signal being reflected by the surfaces of your room. So those sort of things impact the accuracy. So what we do, the step one is we work with an audio front end partner. We don't, Fluent today does not have our own front end solution, but we are partnering with one of the leading solutions. And they take away that workload of removing noise, isolating speech from noise, and giving us a signal that's relatively cleaner. It's not going to be 100% clean, but it's some part of noise is removed, or majority of noise is removed, and some part of speech might also be removed. Because again, the system actually doesn't know what's speech and what's not, but it tries to do a good job. Then the second aspect is we make our model robust to such things, to reverberation, to noise, etc. And that's how we train the model. And that's part of that is how we train the model, and part of that is our technology. That because again, we're not trying to go to text, so the kind of resolution that our models need to predict is a bit different. So they can be more robust to noise sort of situations. So together, with the front end, with the technology and training mechanism, we can create a model that is very robust to noise situations, including wind and music scenarios. Now, the second part of your question related to industrial applications, that's actually very interesting to be able to detect anomalies in different devices and all. But this is not where we are today focused. We are mostly focused on enabling voice user interfaces. Could our technology be extended to that effect in future? Yes. What's interesting is that there are a lot of voice user interfacing applications in industries today. And in fact, one of our partner is BSH in Germany, like one of the leading manufacturer of home appliances. And they are using our technology to automate or to voice enable the manufacturing their factory. So so think of it like on a conveyor belt. You have these large machines, or being a washing machine or something is being manufactured. Now, instead of the user or the controller having to go to a board, press a button, or to move the device up or back and forth, something like this, they could just say that, right? Move up, next, rotate, all those sort of stuff. And so this means that it would, for them, it would increase their productivity. It would save time going back and forth to the controller, pressing, etc. And all those things could be automated just using their voice. And the challenge, why this use case is interesting, is because in factory scenarios, there is a lot of background noise.
Yeah.
And you may have on one factory floor many different people or many different controllers controlling their belts and all. So you got to differentiate between when I am controlling it versus when my person beside me is controlling this. So this is why it's one of the very interesting use case of speech technology. But I think it could really change how manufacturing processes are done. So there's a lot of scope there. There's a lot of scope for innovation, not just voice, but overall innovation in the manufacturing process that's there.
So in that case, you just mentioned, do you have to set up the system training, let's say, specifically for that application?
Yeah, so that's a good question. So we are, our technology is compared to, let's say, Google Assistant or something. They are a general purpose assistant, whereas we are use case specific voice solution provider, right? So if you have a thermostat, we will build you a model that could do all the commands for the thermostat. And if you want something more, we could do more as well. But the primary objective is to be able to control the temperature, control the air conditioning, etc., those sort of stuff. The objective is not to ask the thermostat how far is Mars from Earth or all those sort of stuff. So the system won't do it. So it's targeted. It's going to do 100 or 1,000 specific commands, and within that domain, you can ask it any questions. So same for the factory setting. It's specific to the needs of our customers, and it's the way we work is that our team will interface with the customer, and they would help them design the use case. Say, okay, you need it for a voice controlled microwave based on our expertise, and we've done work in microwave before. Here is what sort of commands you can have. Here is a trained model that you could put in your microwave, right? But a model for microwave would be different from a model for fridge.
Is there a general template that someone can go and implement this model and choose, 15 words, or does everybody have to do a training?
That's a good question.
So what we are working towards is developing use case specific or domain specific products. So that is, we have as a focus area as a company, we have chosen the factory automation, as I was talking about earlier. But beyond that, wearables, home appliances, those as our focus areas. And within those focus areas, we are proactively developing models that could satisfy needs of our potential customers in those focus areas. So, for example, let's consider smart home or home appliances. In home appliances, we know that customers want smart microwaves. Some want smart washing machines, etc. So in some cases we have, in other cases we are in the process of developing models that are ready or satisfy needs for most of the customers in those domains. However, the customers might still, let's say I give you a model for a microwave, it does 50 things. Right now, you could say hey, this is good for me. Or you could say well, this is good, but maybe I want to add another 10 commands, right? So in that case, our engineering team will work with you and give you an improved model that has those additional 10 commands. Currently, this work has to be done with our engineering team. The customer themselves are not able to update the model as of now. In future, we're working toward that step. Yes.
Okay. Yeah, because that's one of the, I think, challenges is to develop your own custom library. But I did notice that you're saying that the training, some other say you need at least 10,000 utterances to try to reach something that has a relatively high accuracy. But I noticed in some of your documents that you're saying that less than 10 hours of effort, and how does that equate, like 10,000 utterances? I mean, 10 hours less sounds pretty good, and also in terms of NRE fees that a client might need to pay in order to get something that they can use on their product. So it sounds like that cost impact could be reduced as well.
Absolutely. So, right, in speech recognition, conventionally, how you measure the amount of data is not necessarily in terms of number of utterances, but in terms of if you were to concatenate all the utterances together, how much speech is that in terms of time, right? So this is where that 10 hours come from. Now, 10,000 utterances is you'll have to make some assumptions, like let's say each utterance is 2 seconds long, et cetera, et cetera. But to get to the crux of it, like using this unique speech to intent technology that we have, it does enable us to create models with much less data than conventional technologies. So conventional ASR-based technologies. We can be very focused. We can also take advantage of models trained in different languages. So when we train a model in English and Mandarin, there's a cross-learning happening in our models during that. I won't necessarily say that the 10 hours, I won't promise the 10 hours one right now, because our models have been evolving lately, and that requirements does change depending on the model architecture. That requirements also changes depending on what the customer's need are. If the customer only wants 10 commands versus another customer, they want 400 commands, right? So those are very different use cases. Therefore, the requirements are very different. But overall, in an ASR system, typically, when you in a conventional speech-to-text-based system, typically you requires about tens of thousands of hours of speech to train the acoustic model, and that's just going from speech to text. Then, in fact, it is not. Sorry, I missed. There's also a part where you have to train the language model in order to go to the speech to text. The language model is a model that basically, if you know the past two words, let's say I said how are, then in your head you're already thinking he's going to say you. But I could say how are the work projects going, right? The probability of that is lower, but still I could say that, right? So a language model is basically a model that predicts based on the 2 or 3 or whatever words it knows. Based on the history, it predicts what's the next word could be. So in an ASR system, it combines acoustic model and the language model to give you the text. And typically, language model is trained on a whole bunch of text data, like entire Wikipedia. It used to be a very popular language model database. And after that, you only have text. And then obviously this training NLP models are in turn new beast as well, right? So there's a lot more data requirements there. Whereas in our case, all we need is only the acoustic data. We actually don't need any text at all. So the language model training, the NLP training, you could just remove that. Our model can directly learn all those things from the acoustic data itself. It learns different representations of, let's say, if I'm saying turn on, so it learns, okay, one person is going to say turn on, another person is saying switch on, and how one person says on versus another person says on is very different. In fact, when I say it twice, they are not identical. So our model learns all that and clusters these sort of acoustic representations of words, and sort of next time you say the command, it knows like, okay, the person said on, person said light, so this is an action being performed on an object like that. So it is considering, or because of this approach, that we're able to reduce the data requirements, and that results in relatively lower NRE or relatively lower effort to train the models.
And that is also means that your machine learning model would allow for potentially more different words on the same processor as somebody that's using the ASR technique.
Absolutely.
You don't need to store the text data.
Right. So we don't need to store the language model component. It also means that, as I was giving you the example, right? So we have a combination of a wake word system, and we call it AIR. So as an ASR, we call it AIR, automatic intent recognition. So let's say you have an AIR system that is to recognize 100 different intents. Then a combination of a wake word plus AIR together can run on a processor only running at 58 megahertz, and it only uses about 99 kilobytes of RAM. So those are very, very small numbers. And so it can run on a Cortex M4, or you could have like 100 intents are actually a lot, right? So 100 different things, 100 different functions for that device, and many different ways of saying those are included in that, right? So that means that typically where you needed a much larger processor, now you can do it on a much smaller processor. Or if you were to consider the converse of it, that means on a much larger processor, you could do a lot more things. So you could have a bigger model doing very many different commands, etc.
Okay. Maybe it'd be, if you had a demo, maybe we could take a look at that. Would that be something we could set up quickly?
Right. So I have a couple of different demos that I wanted to show you. And one of them highlights the small footprint, and the other one highlights the multilingual capabilities of our system, right? So I could share screen and play the demo. We will see how the audio comes out and then go from there.
Full screen this.
Can you see my screen in full screen?
Yeah.
Hi, everyone. So I'm not sure if you will be able to hear the audio here, even though I did select the right option. But see, this is a Cortex M4 board, and it's a board from ST Microelectronics, STM32 Discovery board, they call it. So it has a processor running at 100 megahertz, and we're doing 3 parallel wake words on it. So in this case, Alexa, Hey Google, and computer. So the person could say either of those, and it's doing 50 different commands, and it has this small screen here where we've tried to depict different devices inside a home. So there could be Wi-Fi, there's lights, TV, and the temperature controller. And let's see if you can hear it.
Kilobytes. Here's a bit of a demo. You'll see the screen update when I say the commands. Alexa, Wi-Fi on. Computer, turn on the TV. Alexa, lower brightness. Hey Google.
So you saw, like, the person could say Alexa, computer, Hey Google, and they could mix and match. They don't have to say specific commands with specific wake words. In this particular demo, you could say either wake word and either one of commands, and the latency is very quick. That's another advantage of having something on device, right? So there's no round trip time to the internet server. There's no internet connectivity issue. In fact, this reminds me of an interesting episode so this reminds me of an interesting episode when I was actually in India from November till February, and I had my iPhone, and there is 4G LTE connectivity everywhere. So, and in fact, I was able to take Zoom calls on these 4G LTE, but Siri would never work. I would like, hey Siri, remind me to do something. Mm-hmm. Just like loading. Okay, I'm trying. 4 seconds later, it gives up. So even though there's connectivity, it's just that the connectivity 4G doesn't necessarily mean the same thing going from Montreal to India to Hong Kong to Japan, right? The internet connectivity standards are very diverse. And this is another issue with internet connected devices. So here, not running everything on the devices, we are able to control that latency aspect. In fact, most of our models we try to aim below 300 millisecond of latency. In many cases, less than 100 millisecond of latency. And so for human observer, it's not noticeable difference. So they say like, okay, the action took place right away. And that's been one of the key factor for some of our customers for choosing us. So another demo I wanted to show, and this one is a multilingual demo. Here we have a small device. This one is running a ESP32 device, so 240.
That's the expressive module, is it?
Yes, okay. Exactly.
Yeah.
And so we are only like our model, even though the device is actually much more powerful for what we need, our model is only using 50 megahertz. It's using 512 kilobyte of storage, flash, and 100 kilobyte of RAM. It is doing two different wake words, I think Alexa and computer in this case, and it's doing commands in English, Mandarin, and Korean, and everything on this very, very small module. In fact, for this device, we won the CES innovation, or we were the CES 2020 honorary innovation for this.
Computer, hello. Now change screen red in Mandarin.
So the person, before they give a command, they will, if the command is not in English, they will tell you that they're going to do this in this language.
Alexa, 把屏幕改成红色. Now make screen blue in Korean.
컴퓨터, 화면 파란색으로 바꿔. Alexa, start flashing the screen.
Now stop flashing in Mandarin. Computer, 停闪. Now make screen yellow in Korean.
Alexa, 노란색 화면으로 변경.
Computer, change color to green. Now what time is it in Korean?
컴퓨터, 지금 몇 시?
So you see, like the key thing to see there is how fast it is. It was it's like almost like the person is done speaking. It happens, right? And it is doing three languages, two different wake words, and it's instantaneous on this small device.
So is there two different kind of processes, one to capture the wake word and then one to do the intent?
Yes, so that's a good question. So these are two separate modules per se. So the wake word model is typically very, very small because the wake word model has to listen or to be running most of the time. Right? There could be a voice activity detection module before the wake word model. So see, the objective is to use as little power as possible because most of the devices we are targeting are battery powered devices, right? So we have customers either in a wearable devices like a wristwatch, and we have customers in hearable devices, or even like remote control inside a smart home, a home scenario, voice control, remote control that runs on two AA or AAA batteries, right? The objective is to make sure those batteries last as long as they can. Even though today's smartwatches, most of them, you have to charge every day, that's not very practical. You're just putting up with that. So this is where there are different sort of stages of the system. So very first stage is voice activity detection. If there is no voice, don't run any speech recognition system, nothing at all. The second one is the stages when the person is actually talking to the device, right? So you have to determine when the person is talking to the device, and this is why the wake word is useful. Or the replacement for the wake word could be a push to talk button, right? So when you press the button, now you know the person is talking to the device. So the wake word has to run most of the time when it detects a voice presence to determine whether did the person actually say the wake word or did the person, they're just two friends talking to each other. Now, if the person or the user did not say the wake word, there is no reason to run the big speech recognition engine, the AIR module in our case. And I say big, even though all our systems are very, very small, but still it is still bigger than the wake word module, right? So in order to preserve the power, the AIR module is only run when the system is confident that the user is actually talking to the device. So this cascaded power approach helps the devices last much longer.
Okay.
And so then the intents in that case, are they the whole sentences, or is it just picking out like the colors part of it?
These are whole sentences, right? So the way our system would work is, I could show you another demo where you could have more complex sentences. So instead of just saying, in this one, for example, this was just changing screen to a particular color, but in the other demo, it was setting the temperature to a certain degree in the particular room, right? So there you could have a lot more variability, a lot more flexibility in the system, right? So maybe I will quickly show that demo.
So you're actually able to extract information from that sentence, for example, a temperature, a number.
Exactly. So what our system does is that it's very similar to if in NLP you are familiar with slots, right? So people often who work in NLP, they will talk about slots, right? If I say like, hey, set the temperature in bedroom to 10 degrees, very, very cold. Let's set temperature in bedroom to 18 degrees, so it's a bit more comfortable. And so now the system recognizes like, okay, location could be a slot, right? Bedroom versus kitchen versus bathroom. Each location could have many different objects. TV, radio, thermostat, lights, blah, blah, blah. And then each one of these objects could have different properties, right? So TVs could have volume, TVs could be on and off, so different actions could be performed, different property values could be set. So our system is able to detect and extract that information and recognize that it needs to take the certain specific action for those.
Oh, wow, that's vastly more intense than I initially thought. I was of the impression that you were just triggering on words. Are you actually getting information out of a sentence?
So is it?
Yes, exactly. So
wow.
Go ahead.
So the idea for us, if I were to summarize, is to have these. When people talk about natural user interface, right? So we want to have these natural spoken user interface. So a person, like the machine learning means that the system is learning about the user. If the user has to learn how to use the system, like, I have to say this is specific command, then that's not machine learning. You're learning the machine. The machine is not learning with you, right? To work with you. So that's basically the point. To develop user interfaces where the user doesn't have to think about, is it power on? Is it turn on? What do I say? Like the system should be able to know that and have a very natural way of like the for user. They just go and say the command and the system executes that. So that's the idea.
So it's like there's multiple, almost in a phraseology capture. There's kind of almost like multiple classifiers, and then there would be some kind of perhaps weighting system, as like it recognizes a number, it recognizes a like a room, and then it's maybe to inference what you want it to do from like understanding those key classified or slots, as you called it.
Yeah, absolutely. So that's a good analogy to say that there are multiple classifiers, even though it's not exactly the same, but it's a good way to understand that there's multiple classifiers that are all working together, right? So I could have one, let's say this is a classifier that's going to detect between different locations. This is going to detect between different objects, but objects have a dependency on locations, right? Not everything is everywhere, right? And then this detect different actions. So there are, for these, there are valid combinations and invalid combinations, right? If I say, set the radio to 10 degrees, like if my system detects that is not a valid combination, right? It doesn't exist. So the system also takes that into account. And the thing is, all this, it learns from the data. We don't have to explicitly set any of that information. And this is the one of the coolest part of our technology is that it makes it really easy to design these efficient voice user interfaces. There's no need to explicitly set or what are the different, like for example, in a conventional ASR system, there is this concept of dictionary. So a dictionary is basically pronunciation expansion of, or different pronunciation expansion of the words that the system can understand, right? So one example is democracy. Democracy could be like, if a North American person is saying, they would say democracy. I come from India. I still, to this day, I call it democracy, right? And that pronunciation expansion is very different. So, but if I want to have a model that effectively recognizes both, I need to have those both expansions in my dictionary. But so that's the conventional ASR system way of doing things. In our case, we don't have a separate dictionary or pronunciation model. Our model automatically learns based on the examples it sees. It can automatically learn, oh, here are the different ways of speaking this word. So democracy, etc., different accents. So this is why actually this also gives us an advantage of across different accents. So we have models. In fact, one of our most recent demo that we just shipped to a number of customers, it recognizes English and Mandarin, but also English with North American accent, Chinese accent, and also the users from different places could use it. And these days, like again, we're living in a more and more global world, right? The definition of North American is changing. There's people living from everywhere in all the places. So you need to have models that can understand different accents. As you were saying, you have yourself, you sometimes struggle with this. I myself sometimes struggle with these accents. I say something and the Siri just absolutely doesn't get it. And I don't want to specifically pick at Siri, but it's the state of all the speech recognizers. Yeah.
Right. So, but I think one of the principles is currently everything is developed in a model on a GPU, and then it's translated onto the chip. Now, just kind of maybe looking at roadmap things, like some of the ambition of some of the brands, I think that you and I talked to, is they want it to be able to learn on the edge. And I saw in another presentation you say that this is in the future. Maybe talk about how far away that is, or how you might get there.
Right. So there's two kinds of learning. If you talk about learning on the edge, there's two possibilities there. One is, do you want to train the model on the edge from scratch? Or because if you want to do that on a small device, that's very hard, because typically neural network models are large and they need to crunch a large amount of data to do something, to be able to learn to do something. Right. However, there can be specific cases. You could have a model and then the user could have the ability to tweak the model directly on the device. They should have the ability to personalize the model directly on the device. So some examples of this could be, let's say even for wake work, right? Think about a scenario where, robotic pets, I think they're going to be, people need companionship, right? And robotic pets don't poop. So it simplifies life quite a bit. So in those scenarios, I think there's a big market there, robotic pets, right? Yeah. However, do you think everybody would just call all their robotic pets Alexas? No. Right. People want to name their pets. That's one of the most important things. First thing they think, I want to call this. So in that scenario, a technology where a user could just choose the wake word for their or wake word, trigger word, attention word, the name of the pet is very, very useful. So that's something that is possible today with the right kind of combination. So I can show you
Isn't that a little similar to what they do with Siri? When you first get your iPhone, you have to train it for it to understand your enunciation of Siri, or
that's different, because in that particular case, what you're doing is the word Siri or Hey Siri is the same, right? Okay. But what's changing is that you are training that with your voice profile. So it fires for Dave, but it doesn't fire for Simon, right? Okay. So it's more of so that's personalization as well. And it's happening on the device. That learning is happening on the device. And in fact, the Siri keeps learning over time more and more about your voice to further improve this. What I'm talking about is just changing the word Siri, If you have the phone and you're like, I don't want to call it Siri, I want to call it, I don't know, something fancy like Hey Bob. Not fancy, I know. But it's just say, Hey Bob, Hey Bob, Hey Bob 4 times, and then your device just starts, that becomes the wake word, right? So that's basically one kind of personalization that's possible. The other kind of personalization that is possible is even changing one of the commands. Let's say I bring home a smart home device and it turns the lights on, but I don't want to just say turn on the lights. It's boring. I want to say something else, or maybe I prefer to speak it in Hindi, or maybe even for the door, maybe I want to say, instead of saying open the door, I want to say open sesame. I have kids, let's say, and the kids want to do something playful. Mm-hmm. So right now, there is no way for any of us to be able to do that. But it is possible, like our technology allows us to add that kind of personalization features where the user could give quick feedback on the device. And let's say the device understands 100 things. The device could learn 5 new things directly from the end user. The cool part is that these new commands, or even replacing the existing command, could be in a completely different language. Mm-hmm. And there are other use cases for this, not just like this sort of gimmick. Like, to give you an example, actually the real world example, I have a friend named Sarah Langelier. Now, it's a French Quebecois name, last name. So she goes into her car and she says press the voice button and says, call Luc Langelier, her father. So the system starts dialing, call Luc, but then cancels, because every time she says that, the system misrecognizes Langelier as cancelier, to cancel in French, right? Yes. And she's so pissed. She's like, well, why can I not give feedback to the system to say like, oh, when I'm saying this, I mean dial, don't cancel it every time, right? So these kind of use cases, there are many videos. There's a video on YouTube where a father is trying to turn on, I think it's a Samsung smart TV, it's a TV turn on. TV doesn't. Then the son comes and like, oh, you have to say power on. And it's like, it goes back to what I was talking earlier, that you shouldn't have to learn the machine. If you're doing machine learning, the system should be able to act for both turn on and power on. Or you could be able to change it, right? Maybe, especially in multi-generational households, parents don't necessarily speak English, or if you buy a smart TV for your parents or you're somebody and they don't speak the language, they should be able to change some of the commands. So there are real use cases. And in fact, it's these advantages of our technologies, which is where I see, like along with the other stuff we talked earlier in the call, there is the gap. Like no matter, based on the current technology, it doesn't matter how much you improve it, unless you give people the ability to be able to choose their own words, choose their own commands, etc. Like there's always going to be this gap between fully accepting the speech recognition system, right? So that's where that's being one of the motivation factor as well. So on that note, let me show you a very quick demo of the user trainable wake word that we have. And so it's 50 seconds long. So this is again another one of ST small discovery board. And the idea is that the user is going to press a button, say a command a few times, and then the system should be able to learn from that and then recognize that command as wake word.
This is a demo of Fluent.AI's user-defined wake word solution, which enables a user to choose a wake word of their choice in any language and train the system using just 3 repetitions of the word. So let's give it a try. Fluent.AI, Fluent.AI, Fluent.AI. The training happens on device and the system is ready right away. Fluent.AI, Fluent.AI. I can choose to reset the system and choose another word in another language. Let's go with hi friend in Mandarin. Hi 朋友. Hi 朋友. Hi 朋友. Hi 朋友. Hi 朋友. And there you go.
So yeah, so that's the user-defined trigger where whether that's your smart device, smart pets, etc. People could just name their device They don't need to use text. They don't need to stick with a particular language, just truly natural, universal user interface.
Is it seem like the companies with the ecosystem, like an Alexa or a Google or Apple Siri or Baidu, whatever, it seems to me that if they have home devices that are collecting your speech and then you have edge devices, that there could be cooperation between those devices to help accelerate the learning of your voice. Is that something that you might see in the roadmap of systems where like it's collecting your sound bits and then it's being more accurate recognition or understanding the nuances of what you're saying, etc.?
Yeah, so there are certainly possibilities of interfacing these two types of technologies. In fact, early on, we did work on a set of technologies that we call hybrid, where our system could act as a front end to some of these branded virtual assistants. And in that sense, the system could be doing a number of things offline on the device and responding very quickly, etc., even on a very, very low power device, let's say a HomePod Mini. But as and when the system needs, now it's beyond the user says a command, and then the system detects that it is beyond the vocabulary of the offline system, and this could be handed over to the virtual assistant in the cloud. So certainly that kind of possibilities are there, just even with our standard AIR system. And for the user-defined trigger, obviously the possibilities are you can combine it with any module, any system. So there's infinite possibilities there for sure.
Okay, so one I guess a question that I'm curious about is with the size of the database of Google in terms of the number of words and everything that they know, is it possible for another company with machine learning to catch up to them or beat them using technology such as yours? Is Google already long gone on the machine learning path? Is it? Do you know what I mean?
I think it is. So it's a loaded question, right? And there isn't necessarily one correct. It's not black and white,
right?
But I think it is possible. It is. So there's a few things that's happening. Like the kind of work that we are doing, we're saying that you maybe don't need that much data. And if you think about, as I was talking in the earlier in the call. There are lots of languages around the world. Right now, the speech recognition solutions are mostly only available in North America, Mandarin, North American English, Mandarin, and maybe some other, high profile or more popular languages, right? But there are about 1,500 languages around the world. There's 7,000, 8,000 languages around the world, but there are about 1,500 that have each more than 100,000 speakers, native speakers, right? So now, if the objective is that we want to enable all these different people to be able to interact with their devices or yell at their fridges in their natural languages, then that means the current solution doesn't cut it. And so there's a very active research area in speech itself called low resource languages, where the low resource as in you don't have that much data for those languages. So how do you train systems for those languages? How do you give the same kind of capabilities for those languages? So where we are today with Google and Apple and everybody else is that, yes, data certainly does give them a certain edge. They have done a lot of work in AI and machine learning and all, but we only start at the beginning of this AI puzzle overall. There's lots of interesting research coming out. There's things that we are doing where we actually don't need that much data. There are new kind of techniques coming. So let's see. Let's say there's a language for example, my mother tongue is called Khadi Boli. It's a older version of Hindi, and there's not very many speakers from India point of view, but even small percentage in India is very many speakers. So it's still, there's a lot of people who speak it, but there's absolutely no system that does speech recognition in Khadi Boli, right? But why is that? It's because in order to develop a conventional system in Khadi Boli, you would need to not only get a lot of voice data, but that voice data has to be labeled that the person here is saying turn on the light. But it's not that in this sentence person is saying turn on the light. It's like within this, from this second to this second, person said turn, from this second to this second, person said on, blah, blah, blah. So the data has to be labeled very, like at a very high resolution, and there's some part of that you can automate, but a lot of that has to be hand labeled. So there's effort in collecting the data, there's effort in obviously cleaning, making sure the data is clean, blah, 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 blah. And then there's also effort in preparing, labeling that data. And this is where, these companies that have a lot of data have an advantage because they already have a lot of data and that is labeled, et cetera, et cetera. But now there's, for example, the technique that we use, we don't need this supervision. What we call the technique we use, we call it weak supervision. Basically, we just need high level labels. In this sentence, the person just want to turn on the light, right? Something like this. We just need very high level, so we call it weak supervision. So it's cheaper. It's easier because we need less amount of data, but it's also cheaper for us to label that data because we don't need that same sort of precision. But going beyond and things that we're thinking about, but other people are also thinking about, is these class of techniques called unsupervised speech recognition, where you actually, or unsupervised machine learning, where you don't need the labels at all. And so there's some new interesting research recently came out about that as well. So this allows basically people like us or new entrants in the field is that all they need is now audio data, no labels needed at all. And then they could bootstrap or start the system from that. They might need some small amount of labeled data later, but that amount is much, much smaller. So this is where the advantage of these companies that today have lots of data diminishes over time. Obviously, they're the big players, so they have more money. They could do the same things with, faster because they have a lot more resources, but necessarily it doesn't mean that other people cannot catch up.
Right. Okay. Well, maybe we can tell people how they if they want to work with you and install Fluent.AI on either, I think Qualcomm's doing some voice or Ambic or an ARM core. How would they engage with you if they want to put Fluent on their device?
Absolutely, and so we have been working with a number of different partners. So you mentioned Ambic is actually one of our partner hardware manufacturer, but typically our process is they could contact either me directly at my email, Vikrant, Vikrant at Fluent.AI, or they could go to contact@Fluent.AI, and we get started by first understanding what their needs are, right? So where they are in the development process, what exactly is the use case they are looking for a voice solution. We have some demos that we could send them in order for them to evaluate our technology to get started. But beyond that, we will work with our team, will work with them to say like, okay, you need it for a fridge, you need these functions to be voice addressed. And then we will go and build a model for that. We will take care of the process from there, whether if that involves extra data collection, etc. We do that. We have systems for that. We have partnerships for that. Our engineers will build the model. And the other thing to consider is also and what device the model would be running on. Is it going to be near field where the person is speaking close to the microphone? Is it going to be the far field, etc.? So we have expertise in that, or we have partners who can provide right kind of solutions for that. So we would do this consulting in helping them design the right product. And it's very important because no two voice products are the same. There's just so much variability in this field right now. So our team takes care of that and then basically delivers a finished version, which would be an SDK that is running in the target device. And we then will help the customer with building their system around that SDK, right? So eventually, like our job is to take speech as the input and output some sort of identifier that the customer can take and execute on the device, right? But they know their device, so it's their expertise to do that. And then we help with them with the commercial deployment and all. But yeah, they could get in touch by just a simple email, contact@Fluent.AI. We have demos ready off the shelf. They could use, they could evaluate, and we could go from there.
Okay, great. Simon, do you have any more questions?
Oh, that's fantastic. Thank you.
Okay. Well, all right. So everybody watching, please, do the like, subscribe, share, hit the comments, try to educate us, school us, stump us on some questions. We like that. And Vikrant, thank you so much for joining us today. Really appreciate that. And look forward to seeing your stuff in the market all over the place, probably sometime soon.
Thank you. Yeah, thanks you too. And thank you for the time as well.
Okay.